Okay, so hi everyone, I'm Dr. Stephen Suryasentana. I'm a senior lecturer at University of Strathclyde in Glasgow, and thank you so much to the organizers for inviting me here today. So today I'm going to talk about applications of machine learning in offshore geotechnical engineering, where I will discuss some of the challenges that I see in offshore geotechnics and what are the opportunities I see in having machine learning help us overcome them. So offshore geotechnics is historically important for energy sectors such as offshore oil and gas, but in recent times, the focus has shifted towards offshore renewable energy, such as wind farms. And there are several challenges associated with offshore geotechnics where I believe machine learning has an opportunity to make a big impact. So first of all, the first challenge is that offshore data collection is very costly. And so this often leaves us with very sparse data sets that are very limited compared to the onshore counterparts. And secondly, for large projects such as offshore wind farms, there is an increasing reliance on multiple forms of testing, such as geophysical and geotechnical testing. And because the data that is acquired are of very different nature, it is very challenging to integrate these disparate data sets manually. And also, the design of offshore wind foundations typically involves a mix of high fidelity modeling, such as finite element simulations, and lower fidelity models, such as Winkler or macro element models. So there's a question on how we can actually combine and make sense of these two data set of results in a consistent manner. So to tackle these two challenges, we can leverage some of the more advanced machine learning methods. So first of all, let's talk about the issue of limited data. So here is where physics-informed machine learning becomes very useful, because by embedding physics-based principles such as our understanding of soil behavior or foundation mechanics into the machine learning process, we can exclude the physically unreasonable predictions. And this will help us make much more robust predictions, even when the training data is very limited. And the second challenge is essentially about the fusion of data from multiple sources, which often vary in terms of quality and volume. And here, multi-fidelity modeling can be very helpful in helping us maximize the value of all the available data. And this will help us to get much more reliable predictions. So the high fidelity data provides accuracy, while the low fidelity data provides coverage. So by combining the two types of data, multi-fidelity models provide predictions that are both accurate and scalable. And the underlying technique behind multi-fidelity modeling is to use the low fidelity data to learn the general trends while correcting these trends using the limited high fidelity data. So this approach can significantly reduce the amount of high fidelity data required for training, while still providing reliable predictions over a larger coverage area. So in the next few slides, I will discuss some of the current applications of machine learning in offshore geotechnics. I will focus on three key areas within the offshore geotechnical engineering pipeline, and these are site characterization, foundation design optimization, and real-time predictive monitoring. So for large projects such as offshore wind farms, there is an increasing desire to reduce the cost of site investigations by leveraging more on geophysical data, which are cheaper to acquire than geotechnical data. If you look at the figure on the right, you can see that geophysical testing, such as SBP, provides very high coverage, but they don't actually directly measure the geotechnical properties which are necessary for engineering design. In contrast, geotechnical testing, such as CPT, provide direct measurements of the geotechnical properties that we are interested in, but they are very limited in coverage. So the problem that we're trying to tackle here is, can we actually use the physical data, geophysical data, to predict the geotechnical properties? If yes, then we can significantly reduce the cost of site investigation for offshore wind farms. And to bridge this gap, multi-fidelity modeling can be used to learn the relationships between the geophysical and CPT data at the co-located locations. And once these relationships have been learned, we can then predict the CPT values at the unsampled locations, and this will allow us to have both high coverage and high accuracy. So although this sounds very simple and straightforward, in reality it's a bit trickier because seismic data is very noisy. If you look at the figure on the right, you can see that there's actually no obvious relationship between the seismic data and the CPT data. So for this reason, some researchers have preferred to invert the seismic data into acoustic impedance before applying the machine learning model to predict the CPT data. So the hypothesis here is that the acoustic impedance is more correlated to the CPT data. So this is very much still a very active area of research, and a variety of machine learning models has been trialed for this purpose, including neural networks, co-kriging, and Bayesian compressive sensing models. So now on to foundation design optimization. Simplified models for foundation design are often calibrated for homogeneous soil conditions, and this limits their reliability when applied to layered soil conditions. And unfortunately, layered soil conditions are commonplace in offshore environments. So the problem here is, can we actually use machine learning to provide reliable predictions in layered soil conditions without too much computational cost? So one approach that has been shown to be quite effective is to use multi-fidelity modeling to learn the relationship between a small set of finite element results and the corresponding simplified model calculations. And after the training process has been done, you can then use the machine learning model to correct the errors of the simplified model calculations, and this will provide you with much more accurate predictions with high efficiency. So in this particular paper, we apply this concept for the prediction of the suction casing stiffness. So the figure on the left compares the simplified model calculations in over 400 different layered soil configurations against the benchmark 3D FE results. Evidently, you can see that there's significant errors with the simplified model calculations. So to test whether multi-fidelity modeling offers any advantage over traditional machine learning models, we evaluated 3 different approaches or models for the casing stiffness prediction problem. So the first model essentially is just a traditional Gaussian process machine learning regression model that is trained purely on the finite element results, while the other 2 are multi-fidelity Gaussian process model that are trained on both the FE results and the corresponding simplified model calculations. And if you look at the figure at the center, that's the comparison of all the 3 models, which has been trained on 15% of the full FE data set. And you can see that even with such a small amount of FE data set for training, the multi-fidelity models outperform their traditional single fidelity machine learning model. And the figure on the right actually shows the root mean square error of each model, depending on the amount of training, amount of FE data that's used for training. And you can see that regardless of how much FE training data is used, the multi-fidelity model outperform the single fidelity traditional machine learning model. So what this means is that if you have a wind farm with hundreds of foundations to design for, you don't actually have to carry out many FE simulations in order to get accurate predictions for the entire site. So multi-fidelity modeling provides an approach to get really accurate results, and this means you can save on computational time and cost. And this technique is not just limited to prediction of foundation stiffness. You can also use it for pretty much any foundation response. So in this example, I will show how we can use multi-fidelity modeling to improve upon the inaccurate API model calculations for monopole response to lateral loading in offshore wind applications. So in this particular paper, we actually use data from the PISA case study, which is a joint industry research project that aims to develop new simplified models to predict the monopole lateral response for offshore wind applications. So this case study actually carried out some high quality 3D FE simulations, which are then used to calibrate a new simplified model. In our research, however, we opt to use machine learning to improve upon their API model. So specifically, we developed a physics-informed multi-fidelity neural network to combine the API model calculations with a small set of FE results. And the figure on the right shows a comparison of the predictions of the several models. So the benchmark to focus on is the blue line. So that is the 3D FE model results. The predictions that's closest to it is that of DFNN. So that stands for dual fidelity neural network. So that is our proposed physics-informed multi-fidelity neural network. And you can see that it improves significantly upon the original API model calculations. Next, you can see that the DFNN predictions are much better than the red and green lines. So the green line is the prediction of a traditional single fidelity GP Gaussian process machine learning model that has been trained purely on the FE results, while the red line is the prediction of a multi-fidelity Gaussian process model that has been trained on both the FE results and the API model calculations. So both of these models, if you notice, they make negative value predictions that are physically unreasonable. And this is largely due to the very small set of FE results that has been used for training. So traditionally, one could potentially eliminate these unreasonable predictions by increasing the training data set, but that would mean much more computational time and cost. So instead, what we did here was to basically use our prior knowledge of the physics of the problems to constrain the output to be positive valued, and that helps to enhance the reliability of the model predictions. And the last example that I'm going to talk about is on real-time predictive monitoring during suction caisson installation. So the problem here is that during caisson installation, there are some salt plug hazards that may prevent caisson installation to reach its target penetration depth. And this may result in very costly remediation measures. So the current practice is to use a single beam echo sounder to measure the depth to a single point on the salt plug surface. And evidently, such practice would not provide reliable early detection of the risk of salt plug leak. So initially, we looked at commercially available scanning sensors that can map the entire salt plug surface, but unfortunately, most of them takes too much time for a full scan. So to address this problem, what we did was that we decided to build an AI-controlled scanning sensor, which can automatically decide what is the best data acquisition path to maximize information about the salt plug surface. So this sensor is entirely controlled by a Bayesian optimization algorithm and is able to react to real-time changes to the salt plug surface to scan the critical areas that we are interested in. So we built an experimental rig to simulate the movements of a salt plug surface, and we tested the AI sensor against a conventional scanning sensor. And we also trained a Gaussian process machine learning model on the sensor measurements in order to predict the surface. And the figure here compares the predictions of that model against the true surface. And what you can see is that the machine learning model is able to predict the state of the salt plug surface very quickly. It takes maybe about 2 minutes to get a very good match against the true surface, which compares well against the conventional scanning sensor, which takes about 20 minutes. So with this hardware and software solution, we are now able to get better clarity of the state of the salt flux surface during case installation, which will then allow for earlier corrective measures to be undertaken before critical issues arise. So this proactive approach is valuable for offshore installations where delays and failures can have significant cost implications. So to conclude, we have seen that machine learning have the potential to make transformative impact on offshore geotechnical practices. We have seen how physics-informed machine learning and multi-fidelity modeling can be used to reduce the amount of training data required to get reliable predictions. And this is particularly useful for offshore geotechnics where offshore data collections is so expensive. And so we have seen some applications of these two approaches for site characterization and design optimization. And at the moment, I believe that we have just barely scratched the surface of the full potential of machine learning. And we believe that the path forward is very exciting. And I think it's just a matter of time before we can get a fully autonomous engineering pipeline in offshore geotechnics. So that's the end of my talk, and thank you for listening. And if you have any questions, I'll be glad to answer them.
Thank you. So we do have a question in the chat. I will read it to you. Okay. They're saying that the basic procedure is to collect some data points, create a network model, and then process to release the output. However, it is noted that the available test data in geotechnical engineering is often limited and with high uncertainty. This will have a strong influence on the reliability of outcomes, especially in geotechnical engineering. The question is, what should we pay attention to during the application of machine learning to overcome this challenge, given the example of offshore you presented? And which tool software do you often use to apply machine learning to problems?
I do. So thank you for the question. I do agree with the fact that there's a lot of hesitance, I guess, in using machine learning in actual real application. I guess the right answer as to how do we provide confidence in the application offshore in machine learning on offshore geotechnical applications is validation. It's a bit tricky now because, as I mentioned, the amount of data that's available out there in the public domain is quite limited for validation. But I do see there's an increasing openness for making the offshore geotechnical data publicly available. For example, the Netherlands government has made their offshore wind farms data publicly available. And I think having that is very important because that would then allow anyone to validate their machine learning models. And because it's all open, you can do it and see it for yourself. And I think with time, as more data is publicly available, I would think there would be more people who are much willing to apply machine learning in their everyday workflow. Yeah, so I think that's my answer to that question.
Thank you. So thank you for those fascinating insights into offshore applications. Our next speaker is Dr. Nathalie Dufour from CEREMA, France. Dr. Dufour will present on the use of machine learning for characterization of dynamic ground properties. You can share your screen, please.